In order to convey better with regard to the previous two videos, let's continue. Alright, so this is just a somewhat summary of the previous two videos by explaining to a better extent. Alright, previously, if you remember, we have a L0 and L over the system over here. This system L0 is when it is supposedly the point where it is first built. Or in other words, the system is just being first combined. When you start running, this particular nyquist, the blue color one, alright, will be this system right here. At a long time, due to wear and tear to the plant, the system may actually perturb, may actually change, because the wear and tear actually increase the gain. Alright, increase the gain. Alright, they call this the nominal gain because it somewhat increases the gain by a little. Alright, nominal means that you increase the certain stuff by very minimum or by very little in terms of magnitude. And a long time, this nominal gain gonna add up, right? Add up and it start to move, and eventually it will actually exceed the -1. So now this red color line is simply when you actually sees a certain nominal gain that occur. Alright, and therefore it actually perturbed. Alright, it's actually perturbed or actually moved to a new position. So therefore this blue color is L0 and this red color is L, as shown in this red color one. Alright. We also say that L is equals to CP. Alright, if it's L0, then it's L equals to CP0, I would believe. Alright, it's not C0, P0. It's because the controller is always there. It will not change across time. I mean, in a way that it is just something to control the system, while the plant a long time will change because wear and tear may occur, where you affect the plant's reliability to a certain extent. And therefore, L0 is equals to CP0. Alright? And with this context, therefore, alright, we actually created the understanding of 1 plus L0, which is this distance. Alright, this distance is the most safest distance, alright, where we just first started with our P0, our plant initial. P0 is equals to somewhat the initial plant. Alright, so this distance must be greater than the distance between L minus L0, because L will perturb towards -1 as time goes by. So therefore, the distance between the red color and the blue color is this particular thing, as we say. Alright, so as this range actually goes larger, alright, this distance will be larger than this one, and therefore things goes unstable. Right, we said that before. Because we want to set a percentage between 1 plus L0 and the distance between L and L0, alright, such that when it exceeds, we will straight away know. We want to have a relationship with this understanding. Alright, and therefore this relationship can be used by dividing this whole equation by L0 over JL. Alright, by dividing by L0. So in other words, you're actually setting a percentage between this difference and 1 plus L0. Alright, such as when this thing exceeds, alright, it becomes more than -1, the percentage difference will be very big. Alright, and therefore this is simply this one. Alright, it's exactly the same. After which, we also said that this one can be rewritten as T0, right, which is the 1 over the sensitivity complementary function. And we said that we don't know whether this must be big or small, and now we know that this must be small. Alright, sorry, this is preferably to be big. Alright, preferably to be big, because we know that T, alright, if you were to head back to our previous video, yeah, if you still remember this equation, this is derived from the transfer function where we first started off, and this T, I mean in the way first video, not the previous video. So that because we know that S must be preferably small, because if S is big, the disturbance will be big. Alright, this will disturb your system, and therefore this must be small as possible, and T must be as large as possible. Alright, later on we'll discuss on the little reasons, but just take note that this is preferably big for 1 over T. I mean, T naught must be preferably big, and that's just that one. Alright, so this understanding of relating 1 plus Cp naught to their difference between L and L naught is the Doyle's stability criterion, robustness criterion. And this system, alright, the test for the controller, I would say, if you remember, there is the C and P naught, right? So how does the controller control the P, the plant, a long time? Alright, if the plant gets wear and tear, alright, the controller must have a certain parameters to follow in order to ensure that the plant, be it maybe at time 2, alright, maybe time 2, this is time 2, and maybe 20 years or so, alright, the system may have certain wear and tear, P2. Alright, we have to ensure that this controller C has to keep this P2 has to keep this P2 always stable in some sort. And therefore, to some sense, or to some extent, measuring this using the Doyle's criterion will actually help us see the difference between how the plant would move across time, across certain system. Alright, which then you can see how the characteristic of the controller behaves, right? If the controller along shorter time straight away cause the plant to go haywire, this means that the control is not good. So you need to redesign your controller such that it slowly tahan the plant until the plant fails. Then okay, at least it's nice. Something like that of the meaning. And hence, therefore, Doyle stability robustness is for control, we say, and that it also acts as a bounded system. Alright, they actually bound the distance between your L0 and L within your 1 plus L0, the very larger range. Alright, so you actually bound them at this thing. So this condition actually bound what you are looking at, and therefore creates a better understanding of what is considered robust or not to a certain extent, right? As for now, just now we're talking about L and L0, right? Now we're going to talk about 1 over L0 and 1 over L. And therefore this graph itself, alright, is actually 1 over L0, while should be this case. The green color one should be 1 over L0, and the blue color one should be 1 over L. Be it any of the case. Alright, my fault. the blue color one, alright, is 1 over L0. Alright, because it didn't cross the -1. Alright, it didn't actually encircle. If you were to zoom in, alright, if you were to zoom in, this graph actually goes past, but it didn't encircle. But however, this graph actually encircled the -1 straight away. Alright, and therefore this green color is actually not stable. However, the green color in our case, for example, is actually 1 over L. Alright, and same thing, we do the same method of what we have done for the for the L0. Alright, for this particular system. Alright, we do the same thing over here. Alright, we divided by, instead of divided by L0, we divided by 1 over L0. Alright, therefore it's very apparent over here. And with this trend, you would see that it's actually 1 over S0. Alright, and 1 over S0, this value must be small, right? In order for the disturbance, as we see earlier. Because S is small, then ds, the disturbance will be smaller. Alright, we don't want disturbance at all, right? Now, if you still remember this graph, we have actually briefly said what 1 over L and a high pass, low pass thing. Now I actually write it out in terms of equations, at least it's easier for you to visualize. So 1 over S is simply 1 plus Cp, or 1 plus L0. Okay, why? 1 over S is equals to this one, right? So if you were to divide, you have 1 plus Cp0, just a recap. Therefore I have 1 plus L0 over here, because Cp0 is equals to L0, I would say. Okay, so if that's the case, then 1 plus L0 is, we can just sub in any transfer function k over ax plus 1, for example. Alright, if that's the case, if I were to expand, I multiply the whole thing by as plus 1. I change 1 to this one. This is still 1. And then I add them up together, I would have this form. Now, if the frequency is low, alright, maybe 0 in this case, 0 plus 1, alright, is, so end up you have 1 plus k over 1, alright, so it's dependent on 1 plus k, alright, so k bigger, then you have a slope bigger, something like that. So therefore at the low frequency, which is this portion over here, alright, 1 over s is actually a low pass filter, a low pass system, I would say. Alright, now if it's infinity in this case, sorry, this is infinity plus k. Alright, if in the, like for example 10001 divided by 10000, right, there is this is 100,000 plus 1, this is 100,000. Alright, as you can see, if you to divide, or why not do a better example? Alright, if 1 plus k over as plus 1, if this is 0, then I will simply say that it's 1 plus k. Alright, this 0 means that is low pass, I mean low frequency, sorry. So we're talking about this. Let me repeat again, alright, for this part. Alright, because it's a better explanation in terms of the infinity point. And we know that it's 1 plus k, right? For if the frequency is equals to 0. Now if the frequency equals to infinity, alright, if this is infinity plus 1 divided by k, we are left with only, so this whole thing is 0. So we are left with 1. Alright? So as you can see, if the frequency is equals to infinity, it is k number smaller than yeah, you see? So it's 1 plus k and 1. There is a difference in terms of k, alright, between infinity and 0, right? So therefore at 0, frequency it slowly decreases as k starting to get eaten up by the infinity over here, and then it slowly goes down to 1, alright, which is this part over here, this one, alright. Therefore this is some of the low pass. Alright, now as for this case, which is 1 over t, this is 1 over t, we will have 1 plus L0. Alright, this whole thing is simply plug out. Alright, just now what I have done also is actually plug out from here, 1 over s, then I just rearrange, alright, for the inverse part. If it's 1 over t0, it's simply this one, right? I've shown you how we derive it. I'm just simply taking the formulas and subbing in for you to see clearly the graph how it looks like. So therefore when frequency is equals to 0, this thing will be 0, so I have 1 plus k and k. Alright, when frequency is equals to 0. Now when frequency is equals to infinity, we will have infinity. Alright, and therefore as frequency is at low, at this point over here, or this point is 1 plus k over k. And as frequency increases, it goes all the way to infinity. Just that meaning. Okay? This is also the reason why if t is really high, never mind, I continue first. Alright? Now if you were to combine these two, we will have this one over here, right? 1 over s for this line and 1 over t for this line. Alright, and we have a crossover region over here, where this is the part where we don't want it to actually die off. We don't want the power to actually die off. We want to constantly keep it stable, or some sort of it. Alright, therefore this is actually called the crossover region. Alright, and it's a critical frequency region, right, where this is somewhat over here and this somewhat over here. And this critical frequency region, it relates to this inequality over here. Alright, this 1 over t0 simply relates to here, right, of this region, and therefore this region is good, so I give a thumbs up. Right, and then this region is good, for 1 over s. If for 1 over t, this is for 1 over s. Alright. While the rest that is really in small power, we are actually not interested. Alright, they are not fine. They are not fine. They are not good. Alright. And please do not be confused with the graph of s and t. Alright, s is by itself is a high pass, t by itself is a low pass. Alright, we have proved to you in the very first video of lesson 2, or second video of lesson 2. So therefore, this is not to be confused. Alright, I repeat again, this is not to be confused with this term. Sorry, with this task over here. Be very careful about that. Later on, in the later part of the videos, we'll also talk about something of this graph. Alright, we'll talk about this thing. So please do not be confused with 1 over s and 1 over t with s and t. Their graph is totally opposite. Alright, and the understandings will be opposite. I mean, to a certain extent. So yeah, see you next video.